so first things first, I'd like to thank Hoju for organizing this fantastic series of geometric analysis festivals. I've been really enjoying them. And also for giving me the opportunity to share my work here with all of you. The title of this talk is The Jacobi Spectrum of Null-Torsion Holomorphic Curves in the Sixth Sphere. And maybe there are some unfamiliar words in the title, so throughout the talk, I'll have to define the various words. Most of these are easy to define. The only maybe challenging term here is null torsion, but we'll get to that in due course. Roughly speaking, this is a talk about a class of minimal surfaces in the round 6 sphere, and we're going to be considering their second variation of area. So to set the stage, we're going to begin with some generalities. We're going to talk about minimal surfaces just in general. We're going to review the definition. We're going to review the second variation of area, and explain how that's encoded in an operator known as the Jacobi operator. And so the spectrum of that Jacobi operator is going to be our primary object of interest. To give a sense of the types of results that are known and the types of results that we're maybe going for, I'll mention just a few of the results known for minimal surfaces in the 3 sphere and the 4 sphere. Okay, then we'll specialize to the case of interest today, which is that of the round 6 sphere. Okay, now why would you be interested in the 6th sphere of all spheres? Well, it turns out that among all the n spheres, with n at least 3, the only one that can admit an almost complex structure is the 6th sphere. So what we're going to do is take the round 6 sphere and equip it with its so-called standard almost complex structure. This standard almost complex structure is compatible with the round metric. And with respect to that, we're going to study the holomorphic curves in the 6th sphere. And it turns out that holomorphic curves in the 6th sphere are automatically minimal surfaces, so you can ask all the usual minimal surface questions for it. In particular, you can ask, what is the spectrum of the Jacobi operator? Okay, this turns out to be a pretty hard question in general, so we're going to restrict attention to a subclass of the holomorphic curves known as the Null-Torsion holomorphic curves. And here you should think of torsion as being some sort of analog of the torsion of a curve in R3. And indeed, we're going to define the torsion of a holomorphic curve by using a so-called holomorphic Frenet frame. And it's going to be a little abstract, but to make everything more down to earth, we're going to spend 2 or 3 minutes reviewing the familiar Frenet frame for curves in R3. That way we can more clearly see the analogy with the setting of holomorphic curves in S6. Okay, finally, I'll state the main results about the Jacobi spectrum of null-torsion holomorphic curves. I'll also very briefly sketch the proof. Okay, both of the proofs. Then I'll mention some work in progress, as well as indicate some further interesting open questions. Okay, so let's get started by setting some notation. So this is notation I'm going to use throughout the entire talk. So sigma is always going to be a closed orientable surface of genus G and area A. M will be a Riemannian manifold, and its metric will be denoted by angle brackets. Okay, for us, minimal surfaces are types of immersions, so I'm not going to be considering branch points. Okay, so a minimal surface for us is an immersion that is, well, critical for the area functional. In other words, for any variation of the minimal surface, the derivative of the area at time t equals 0 is 0. So what this means is that minimal surfaces are area minimizing to first order, but not necessarily to second order. So how can you encode the extent to which a minimal surface is or is not area minimizing to second order? That's captured by the so-called second variation of area. Okay, so to recall that formula, we need some more notation. Again, this will be enforced for the entire talk. So d bar will be the Levi-Civita connection of M. dt is the tangential connection. d perp is the normal connection. And Roman numeral 2 is the second fundamental form. Okay, so the second variation of area formula goes like this. Let U be a minimal surface, and let UT be a variation of U with normal variation vector field eta. Then the second derivative of area at time t equals 0 is given by this integral here, and this integral has 3 terms. Okay, so the first of these is a second order operator. It is the connection Laplacian for the normal connection. B is a 0th order term, and it's essentially the second fundamental form of the immersion. R is also a 0th order term, and it's basically the curvature of the ambient space. Okay, so here are the explicit formulas for these operators. They're phrased in terms of a local orthonormal frame, oriented orthonormal frame E1, E2. Okay, so let's give this operator a name. We're going to call it the Jacobi operator. So this is the Jacobi operator of the minimal surface U. Okay, it is a second-order linear differential operator. It inputs normal vector fields and outputs normal vector fields. So we'd like to study this operator. So how will we do that? Well, from linear algebra, we know that a good way to study an operator is to diagonalize it. Okay, now these are infinite dimensional spaces that we're working with, but fortunately, L is a strongly elliptic operator. So by standard theory, it can be diagonalized, and its eigenvalues form, so it has an increasing sequence of real eigenvalues, and their multiplicities are finite. Okay, so we're going to call their eigenvalues lambda 1, lambda 2, etc. Okay, and their multiplicities m1, m2, etc. So the Jacobi spectrum of U is not just the set of eigenvalues, but also their multiplicities m1, m2, etc. Okay, so many well-known invariants of minimal surfaces can be phrased in terms of this spectrum. So for example, the Morse index of a minimal surface is the dimension of the space on which the Jacobi operator L is negative definite. Right, now basically the Morse index is measuring the extent to which the minimal surface is not area minimizing to second order. Okay, so the Morse index is just equal to the sum of the multiplicities corresponding to the negative Jacobi eigenvalues. Okay, similarly, the nullity is the dimension of the space on which L is 0, so that's just the multiplicity of the 0 eigenvalue. Okay, so following standard terminology, we'll say that a minimal surface is stable if all of its Jacobi eigenvalues are non-negative, and unstable if it has a negative Jacobi eigenvalue. Okay, so ideally for a minimal surface, what you'd like to do is just sit down and compute its Jacobi spectrum. But this turns out to be extremely difficult, if not impossible, in the vast majority of cases. So what geometric analysts like to do instead is estimate the eigenvalues and their multiplicities, maybe the Morse index, in terms of more familiar geometric and topological quantities. And that is the type of thing that we're going to do today. Okay, so let's specialize to the case of interest, which is that of the round sphere, okay, where the ambient space is the round sphere, and for us, the round sphere always has constant curvature 1. Okay, so what is known about minimal surfaces in round spheres? So a classical result is due to Jim Simons in '68, who showed, among other things, that a minimal surface in the round end sphere is always unstable. Right, so it always has negative Jacobi eigenvalues. In fact, its first Jacobi eigenvalue is negative 2. Moreover, Simons proved an index bound. He showed that the index of U is at least n-2, and equality holds if and only if your surface is the equatorial 2-sphere. Moreover, the nullity of U is at least 3 times n-2, and again, equality holds precisely when U is the equatorial 2-sphere. Okay, so it's an interesting question to ask about the maybe the next simplest piece of information, which is what is the multiplicity of lambda 1? Well, what can you say about m1? Okay, so an interesting result was proved in this direction by Agiri in the 80s, who considered the case of even-dimensional spheres, so let's say n is 2k, and the case where the surface, sigma, has genus 0. Okay, so this is the setting of minimal 2 spheres and even-dimensional spheres, and Agiri proved this lower bound for m1. He showed that m1 is at least the area over pi plus 2 times k minus 3. Okay, it turns out that Agiri's proof, this is the way that he stated it, but it turns out that Agiri's proof actually, when you analyze it, yields a little more information than just this. That point is going to be important to us later, so we're going to revisit this, and this is one of the motivating facts for this talk. Okay, so I want to mention also some results known in low codimension. So in the case of minimal surfaces in the 3-sphere, there's a well-known result due to Urbano, which basically improves Simons bound. So Urbano shows that if U is not the totally geodesic 2-sphere, then the Morse index of U is at least 5. And moreover, equality holds if and only if U of sigma is the Clifford torus. And this characterization of the Clifford torus as the minimal surface in S3 with the lowest Morse index other than the totally geodesic S2, this was used famously by Marquez and Neves in their solution of the Willmore conjecture. Okay, so there's a lot of interest in really understanding these better bounds for the Morse index and this sort of thing. Okay, but for us, a lot of our motivation, somehow minimal surface, these holomorphic curves in the sixth sphere are somehow, in a way, similar to certain types of minimal surfaces in the fourth sphere. And so the following results are in the fourth sphere are very motivating for us. So let's consider the case of minimal surfaces in the fourth sphere. McAuliffe and Wolfson proved the following very nice lower bound on the Morse index. They proved that the Morse index is at least 1/2 times the area over pi minus the Euler characteristic. For minimal surfaces in the fourth sphere, it turns out that the area is actually a topological quantity. It can be phrased in terms of the Euler characteristic of the normal bundle. So this really is somehow a topological lower bound. Okay, they actually prove this in a more general setting than just S4. They just need their ambient four manifold to have some sort of positive curvature condition, but let's just focus on the fourth sphere case for now. Okay, so unfortunately their bound is not sharp. It's not sharp even for the case of the totally geodesic S2, and one might hope that maybe in special cases, we could do a little better if we, maybe restrict attention to certain types of minimal surfaces. And that's exactly what's done by Montiel and Urbano, who consider a very interesting class of minimal surfaces in S4 known as the infinitesimally holomorphic surfaces. Infinitesimally holomorphic is sometimes known as superminimal. And basically what this means is that the second fundamental form of such an immersion has extra symmetries. It has the same symmetries as that enjoyed by a complex curve in C2. So if you assume this extra condition, then Montiel and Urbano are able to prove, rather precise results. In fact, they're able to calculate explicitly. They get a very nice explicit formula for the Morse index because they note that, in fact, there's only one negative Jacobi eigenvalue in this case. The only negative Jacobi eigenvalue is -2. Okay, so the index therefore must equal M1, and in fact, M1 equals precisely the area over pi minus the Euler characteristic. They also get a lower bound for the nullity. They get this lower bound. It's the nullity is at least area over pi plus the Euler characteristic, and this is sharp. This is an equality when the genus is 0 or 1. Okay, this result of Montiel and Urbano is very much somehow the inspiration for what it is that I'm going to talk about today. Okay, another interesting result that was obtained actually rather recently due to Kussner and Wang, who considered the case of tori, and they were looking for sort of a higher codimension version of the result of Urbano, and they succeeded. They showed that for a minimal torus in the fourth sphere, the index of such a thing is at least 6, and equality holds if and only if U of sigma is a Clifford torus in the totally geodesic S3. Okay, so we're going to turn our attention now to the case of minimal surfaces in the sixth sphere. Now, okay, so again, why the sixth sphere? Well, it's a classical fact that the only spheres that can admit an almost complex structure are the 2-sphere and the 6-sphere. Okay, it's a famous open question as to whether the 6-sphere admits an integrable almost complex structure. That's obviously very hard. So here we're just going to give S6 its standard, certainly non-integrable almost complex structure. Okay, and this almost complex structure on S6, you can describe it in a couple of ways. I like to think of it as coming from the imaginary octonions. So we're going to view S6 sitting inside R7 in the usual way, and we're going to think of R7 as the imaginary octonions. And then this almost complex structure on S6 is just given by the so-called 7-dimensional vector cross product. Okay, and what is that? That's just 1/2 PV minus VP, where this product here refers to octonionic multiplication. Okay, we're imagining everything as sitting inside R7 here. This almost complex structure, we like it because it has a very large symmetry group, and in fact it is compatible with the round metric, so that's good. And whenever we have an almost complex structure compatible with a metric, it's natural to then write down the corresponding. You can call this a Kähler form, you can call this a Hermitian form, but you get this 2-form omega, and it's given by the inner product of Jx with y. So you get somehow this standard package on S6 the triple consisting of the metric, the almost complex structure, and the two form, and this triple of data, this is called an almost Hermitian structure, okay, or a U3 structure if you like the theory of G structures. Okay, so this is what we get by working on S6. Okay, and recall that our notation was that d bar is the ambient connection, so it's the Levi-Civita connection on S6. Okay, so unfortunately, this almost Hermitian structure doesn't have all the nice features that one might want, maybe, right? It's certainly not Kähler, for example, and it's not Kähler for a variety of reasons. Omega is not closed, so omega is not a symplectic form. It's non-degenerate, but it's not closed. J, as I said before, is not integrable, and it's also, consequently not parallel for the Levi-Civita connection. Okay, so this seems, pretty terrible. Why would you ever want to work with this sort of thing? Well, the good news is that this triple is nearly Kähler. Okay, and nearly Kähler means very far from being Kähler is what you should think. There is a sense in which nearly Kähler is somehow close to Kähler, but it's sort of a very abstract type of thing. But what nearly Kähler means for us is that although d bar of j is not 0, d bar j is skew symmetric. Okay, so there's some sort of symmetry here. Okay, so using this fact, you can cook up a new connection on the tangent bundle of S6, and we're going to call this the nearly Kähler connection. And what you do is you take d bar xy and you just add this extra term. And the reason we like this is that somehow this nearly Kähler connection, it plays better with the geometry, okay, because it preserves this entire triple, okay, and then this somehow nearly Kähler connection it's a much better connection oftentimes to work with when you study objects in the sixth sphere. Okay, so since we have this data, we have a J on the sixth sphere. With respect to the J, the almost complex structure, we can define an interesting class of surfaces known as the holomorphic curves. So let's say an immersion, U from sigma to S6 is a holomorphic curve if its tangent spaces are invariant under J. Okay, an equivalent condition that may be familiar to some of you who are familiar with complex geometry is that the two form omega restricts to the tangent spaces to be the volume form. So this looks like we're saying that a holomorphic curve is calibrated for omega. It looks like omega is a calibration. It does in fact have comass 1, but again, omega is not closed. So these things are definitely not calibrated submanifolds for omega. Nevertheless, they are minimal surfaces. Okay, so all the holomorphic curves in S6 are minimal surfaces, and there's a couple of ways to see that. Here are two different sort of sketches of proofs that I like and find enlightening. So one proof goes like this. Suppose you have a holomorphic curve. Then, in fact, you can sort of see without too much work that this implies that there are extra symmetries in the second fundamental form. And those symmetries imply that the trace of the second fundamental form is 0, which means that the holomorphic curve is minimal. So you can just write it down. But another way of seeing this makes connections with G2 geometry. So there's this fact that if you have a surface in S6, a surface in S6 is a holomorphic curve if and only if its cone, that's a three-dimensional object in R7. Okay, so the surface is a holomorphic curve in S6 if and only if its cone is associative. Okay, so associative threefolds, these are central objects in G2 geometry. I won't go into what it means, but suffice it to say that associative threefolds are calibrated submanifolds, okay, that are very, very important in G2 geometry. So the point is that if you have a holomorphic curve, then its cone is calibrated, hence homologically volume minimizing. So the link of that cone, namely the holomorphic curve, must be minimal. So that's another proof of minimality. Okay, so since holomorphic curves are minimal surfaces, we can ask all the questions we like to ask about minimal surfaces. So in particular, we can ask about their Jacobi spectrum. Okay, so what can be said about the Jacobi spectrum for holomorphic curves in S6? Okay, so let me remind you of what's known in general for minimal surfaces in S6. We have the result of Simons that lambda 1 is -2. We know that the Morse index is at least 4, and the nullity is at least 12. We also know by work of Agiri that in the case where the genus is 0, then the first multiplicity is at least the area over pi. Okay, so this is what we know, and we'd like to do better than this. And the question of this talk is, can we be more precise? Okay, so this is probably a good place to stop, leaving the audience in suspense. I'll see you in the next video where we answer this interesting question.